class. Thank you for your patience, and while I've been sick, I'm still coughing heavily every once in a while, so I'm going to still record this video for Thursday, 9 a.m. And what we'll first discuss is the extra assignment that has been posted, homework 3, that's due September 21st at 9 a.m. That's the third homework. Make sure you do turn in the homework 2, which is going to be due on this Friday by midnight. So that gives you an extra day to do that, and you can contact me and ask me questions about any of the aspects of the homework during that time. Hopefully you got in touch with Wance on Wednesday regarding the homework, but you can also contact me by email, and we can also video chat if you have questions about the homework before it's due on Friday at midnight. Happy to talk to anybody, anytime. Okay, and the other thing I want to mention is the exam is now listed, but you can't see the actual exam yet. So exam 1 is going to start on September 26th as a take-home exam through September 28th. And that's when it will be due, is on that September 28th at 9 a.m. And it will be like the homeworks in that it will be an online exam that you'll post solutions to, so that it's easier for me and Wance to grade it. The other thing I want to mention, in case you missed it last time, for the last lecture, I didn't record my own video. I was much too sick on Tuesday, coughing every few minutes, and didn't really have much of a voice. So if you go to the pages and look at special lecture material, you'll see that there is a couple videos regarding the lecture, and then there's the Khan Academy link, which if you click on, it will go through work and energy and related principles that are relevant for the lecture from last time. So please do look at those. I'm assuming that you have watched these videos, and we'll catch up with that next time. So that's it for as far as the Canvas Elms. I hope that you have, Lance said that he would have your grade from the last homework already. So please let me know if that hasn't been done. Please let me know if it's not been graded yet, and I'll get in touch with Wance. Okay. So that completes this. So now let's go back and talk about what we were doing last time. So I'll quickly go over this. Very last thing we were doing is we were talking about how if you threw some silly putty at a stationary turntable, how you could make that turn. And so this particular torque that is applied comes from the R cross F applied at this edge where the putty is thrown to and sticks to. And just using the angular momentum effectively of this little putty relative to the center of the rotation of the frictionless disc, you can use that conservation of angular momentum with a moment of inertia to deduce the the rotation rate that it would eventually run at or turn at based upon that, all the other parameters. So like the mass of the putty, the mass of the turntable, the velocity that you threw it at, the effective impact parameter B, the distance from the center to the perpendicular position, and over r squared, the radius of where the putty is and the size of the disk. So yeah, that's good. So that's what we did last time. So now just want to mention one other example, which is the so-called struck dumbbell. So in this case, we have a dumbbell which has two masses on each side, and a force is going to strike the left part of the mass on the dumbbell, which is separated by distance 2b. So in this case, we can do a very similar calculation. The dumbbell is a different moment of inertia than the disk. It's a sort of more trivial and easy to understand moment of inertia, just summing up the masses in an appropriate way. And we're going to look for the change in the linear momentum in this case. So you can start with the initial momentum as 0. The final momentum will be the total mass and the velocity of the center mass. And that final momentum will also correspond to the force over the time interval. And this is the final momentum because the change in momentum is just the force over the time period of the force being applied. Forces can't be applied instantaneously. There's no significance to that concept. A force must be applied, of course, even in your experience, over some time period, even if it's very short. A force applied over a 0 time period does nothing. It imparts no momentum. So we take that change in momentum, just sort of delta P over delta T is the meaning of force. It's P dot is force. So we just express that as a differential. And now, since the initial momentum is 0, we can express the final momentum as just the total mass, like we talked about before, the velocity of the center mass, which is r vector dot, equaling the total change in momentum, because the p final minus p initial is just p final. And then you can solve for the rate of change of center mass from this equation, and you just divide by mass. So the change in the total angular momentum about the origin then is going to be due to the torque, right? We're pushing it on the edge. So the magnitude of the torque is going to be r cross f. R in this case, because the total distance is 2b, the distance to the center is just b, and so r cross f is just fb. And then we can look at the total angular momentum change. Again, in a differential sense, torque is dl dt, or L dot. But we can look at it, since we're doing the constant force over a given period of time, we can just write that angular momentum change as the magnitude of that torque times delta t, which is equivalent to L dot equaling the torque. Just expanding out that differential, or that infinitesimal differential, into a finite differential. And I can do that if the torque is constant over that time. And we can do that because the force is constant over that time. So we can just write that out, and in the end, we know that because the initial angular momentum was 0, the change in angular momentum is just the final angular momentum, which is now the moment of inertia times omega. And the moment of inertia to the dumbbell case is very simple. It's just 2m times b squared, which we'll call the total mass times b squared. And then, so we now have that moment of inertia. We can plug that in to I and solve for omega. So we get that omega is whatever the force, constant force was, times delta t, over the total mass times the distance to the center of the dumbbell. And so this is pretty useful. So now what we can do, now that we have the angular velocity, the question is what happens actually to the velocity of. So the velocity of that left piece of mass is going to be just the center of mass motion plus the individual motion on top of that due to the angular rotation. And so we know the center mass has been pushed by f delta t over m from our previous calculation, and we know omega now. So we can just plug in omega, and we get one expression, which is that, well, it's just F delta T over M, a little mass. So that's interesting. So it's as if the force was just applied to that little mass. And that's the velocity of the left guy. The right mass initially has a velocity so that the right guy is initially 0. And as I say here, the center mass moves vertically up the y-axis while that dumbbell rotates. So let's move on to the next topic, which was covered in the Khan Academy videos. And I'll move more quickly through this one since you probably, hopefully, watched those videos. The basic idea is we need a concept of energy now, because there ends up being a concept of conservation of energy. And the background of that is that conservation of momentum is not quite enough. Conservation of momentum comes from essentially Newton's laws, or you could say Newton's laws comes from conservation of momentum. But in general, energy is an important concept coming from the conservation of, well, is the conservation of energy, if energy wasn't conserved, then we really wouldn't be talking about energy that much. The fact that it is conserved means that you can analyze a before and after sequence just like momentum and identify variables, quantities from it, like the velocity. You can derive the velocity out of conservation of energy. There are usually two kinds of energy, kinetic energy and potential energy. And in the case we're going to study, for each particle, the kinetic energy is just often called Ke or T, and it's 1/2 mv squared. You can do things like take the time derivative of the kinetic energy, and you get how it changes with time. And if you eventually use Newton's second law, you can show that the differential change in energy is just the force applied dotted into the differential position. So that if you integrate the kinetic energy, it can give you a integral over force over some path. And this is what we call work. So work is defined, differential work is the same thing as above, but it's applied to the force, and the total work is just integrating over a path. So if we have 2 points and we have a path between them, then the total change in energy will just be due to the integral of the force applied along that path with a vector, whatever force vector that is, but it's dotted into the position vector, which is always pointing along the line, what we call a, instead of being perpendicular, it lies along the path. So you can do that integral in any situation, and by finding out that work, it allows you to understand the change in energy and how it relates to the force applied. So one example calculation is you can imagine, given an x and a y position, we might have a path which is like a quarter circle. And we can imagine applying some kind of force along that path. So here's how the path can be described. We have a position vector, which is the position from the center of the origin to a point along that path. That's the r vector. And that's just going to be 1 minus cosine theta for the x position. So theta equals, in this case, theta equals 0 for this theta. Then we have cosine of theta, which is 1. And then so this is 1 minus 1, which is 0 for x. And that's correct. And then y is sine theta. So as we increase theta, the x position goes from being 0 to 1, and the y position goes from 0 to 1. And it happens to be a circle. The differential distance, you just take a derivative of this position, and the differential position is just sine theta cosine theta, all times d theta. So this is just, this parentheses denote a vector. And the whole thing, the whole vector, both components are multiplied by d theta. So we can pull that out. That's the way it works in this notation. And we can have a force that we apply, which we're going to say is just y x hat plus 2x y hat. This is an arbitrary force. It can be anything. So we can do this integral. We just basically use what we have up here as the work integral. The work integral is just integration along the path of f dot dr. Just using the vector notation, we have this is the f vector in its full form as yx hat plus 2xy hat. And we're going to dot product that into the dr, which is just, as we set up here, sine theta, and then this is x hat plus cosine theta times y hat, all times d theta. So now we have a dot product that we need. And we can do the dot product, expanding things out. So we're going to, we can do this in different ways. What we were going to do is we can say, for example, we can rewrite this by having the same term for the dr, but this can be written as a different kind of integral where y has been replaced with the appropriate angle. As above, we have the path was was in the x direction 1 minus cosine theta, in the y direction sine theta. So we can replace y, which is what this r means, r vector means, it's x hat plus y hat. So y is just sine theta. So we can replace y by sine theta, replace the x by 1 minus cosine theta, and then we have everything now in terms of theta. And because our differential for integrating is in terms of theta, that works very well. And we can now do the dot product between x and x hat combined to get one term, and the y hat and y hat combined to get another term. X dot y hat is they're orthogonal, they're 0. So that product is 0. And we can eventually do this integral, it's not too difficult, and we get 2 minus pi over 4. So this is just showing you in detail how to get the work from a specific path that you have to do. First step in identifying the integral and how to do it is to first maybe draw a picture or use whatever information they've given you. And then you have to identify the radial vector corresponding to a position along that path. You have to then differentiate that radius vector to get dr. You have to identify the force, and you may have to do some change variables using the position vector to get rid of x and y or whatever z. Get it all in terms of one variable so that you can integrate it. Right. So the other thing we can say is that there are certain special kind of forces. If you happen to have a situation where the work performed on a particle, say traveling from point 1 to point 2, depends only on, say, the location of 1 and 2, and not the path, or the velocity, or time, then we say the force is conservative. And that basically means that the work done is path independent. It doesn't matter how you do it from A to B, what path you take. That's irrelevant. The only thing is where you started with and where you ended up. And you can, if the force is conservative, it turns out, and so is path dependent, it actually allows you to do a mathematical trick to say that then the curl of the force, which is what this is representing, must be 0. And you can prove that via so-called Stokes theorem, if you remember that from calculus. So I'm not going to go through that proof here, but you can go through that. And I'm skipping a few things since this is done in the Khan Academy. A non-conservative force is a different kind of force, which, well, in that case, it's definitely dependent upon your path, or it could be dependent upon your velocity, like a frictional force could be. And so this is basically saying that, well, is the work energy theorem, the work description in terms of force over the path, useful, even when there's non-conservative forces? And it is. You can identify the total work done as separated into a conservative and non-conservative piece. This is somewhat arbitrary, but it can be useful. And the conservative piece can be understood as that due to the, say, change in the potential, where the non-conservative piece could be due to friction or something like that. And the total change in energy, which is the total kinetic plus potential energy change, would be equal to the total work done by the non-conservative force. And that could be like a frictional force. And what that basically means is that, well, as far as, say, a block or something moving along a path, the total kinetic and potential energy contained in the block is not conserved. But that's only because the frictional force, say, into the ground or desk. And if you include all of that, then of course still energy is conserved. So if you put the work non-conservative on the other side, this whole total sum will still be zero. So let's look at a block sliding along an incline with friction. This is the classic case. So in this case, we have our incline at angle theta. We have a force which is pushing back, gravity which is pushing down, and the normal force that's related to friction. And so what we're going to look at is, well, let's suppose that we have a uniform gravitational field, so gravity is just minus mgz hat. And so we can calculate the potential energy of the block, which is just mg times z minus z naught. Now, if we start from rest at a height z, from the bottom of the ramp, then we can say that the initial potential energy is mgz. The final potential energy is 0. The initial kinetic energy is 0, but the final kinetic energy is 1/2 mv final, of course. Now that we know the kinetic energy is 1/2 mv squared. So the change in mechanical energy must be totally due to friction. So we can say that the total change in energy is the kinetic energy minus potential, which is that frictional force. We know the frictional force is just F equals mu normal force, which is mu mg cos theta, like what we talked about before. And the work then is, since this is a constant force, the angle doesn't change. That means that we can just integrate that over the path. That's the distance traveled along that ramp, d. And so that's the frictional work. And from that, we also know that the height, z, was just d sine theta. So then you can plug all these things in and solve for that final velocity. So you can use the fact that you do have the work energy theorem. You can use the fact that there's a frictional force, and it has work associated with it, to derive, in this case, what the final velocity was. This is just one example. So that basically completes the last end of that lecture. It's been about 24 minutes for that last bit of lecture. And so what I want you to go see now, before we move on to the other lecture, is an example of that on YouTube. Instead of showing you the video directly, I'm going to show you show you the link of what I would suggest looking at if you have more questions. This is a little bit better graphics than I have. So let me go to the point where we see the let me actually show you the picture that I wanted. Maybe I This is the correct video, but I'm not sure where the picture is. Give me a second. I can't find the picture. So anyways, I recommend checking out some of these videos for more information.